zinc oxide nanostructures by temperature controlled non-catalytic growth process on a steel alloy substrate. I am Ahmed Umar from the Jammu National University. I am a PhD student there. Before starting my presentation, I would like to introduce some general properties of zinc oxide nanostructures. As far as the zinc oxide is concerned, it is a very useful and versatile material which is applicable in various applications due to its variety of properties. Like it has a direct and wide band gap which is about 3.37 electron volt. In addition of this, it has a high breakdown strength and large excited binding energy, which is larger than other semiconductor materials like zinc selenide or gallium nitride. In terms of its structural characteristic, it has a non-centrosemitic structure, which is very important for piezoelectric property. Because of this non-centrosemitic structure, it is applicable to fabricate some piezoelectric devices and some actuators. Furthermore, it is also biosafe and biocompatible, and it can be used without coating for further biochemical applications. The low threshold intensity, high chemical stability, and low growth temperature of this material, zinc oxide, make it an important material for future research and application. Because of these various properties, it also have various applications. Like it can be used for displays and some signals, automotives, and also LEDs and TFTs, SAR devices, varistors. Recently, it shows its versatility in the sensors and hydrogen storage. So, because of its biocompatibility, it can be used as a biosensor, and it also can be used as a chemical sensors and gas sensors to fabricate some FET devices and other. The objective of our research work is to grow highly crystalline zinc oxide nanostructures by the non-catalytic growth process on some special substrate like steel alloy substrate via the thermal evaporation process, and to determine its growth mechanism and also its structural and optical properties of these structures, and to determine the substrate temperature, zinc and oxygen concentration during the reaction process inside the reactor. What the impact on these reaction parameters on the morphology and structure of these nanostructures? We also determine this in this presentation. From the common substrate, we use some different substrate in the synthesis, the steel alloy. We choose this substrate because of some interesting phenomena of this substrate. In some cases, this substrate can use as a catalyst, and because of this new substrate, it's very interesting to determine its growth mechanism. And the steel alloy substrate, because the surface morphology of this steel alloy substrate is some rough, which provide an excellent interaction between the substrate and the deposited materials. And this is a harder substrate compared to other substrates with a higher melting point and resistant to acid corrosion. This is our systematic diagram for the experimental setup which we use to synthesize our glucose and nanostructures. Here in the middle of our tube furnace, we placed a small quartz board containing the metallic zinc powder, which we used as a source material for zinc in this synthesis. And we placed three substrates, this indicated as A, B, and C, beside this quartz board. During the synthesis, we observed the reaction temperature at each substrate. So we got that at each substrate the reaction, the temperature was different. At substrate A, we got the temperature was 550 to 525 degrees centigrade. and the substrate B lies in the temperature between 525 to 490 degree, while the substrate C is lies between the temperature 490 to 440 degrees centigrade. So we got some interesting morphologies at on different different substrates, depending on the temperature of the substrate. At position E, we got this, we can say the awake like or archin-like structures. It contains a high density of zinc oxide nanowires with a high aspect ratio. We can see clearly that these zinc oxide nanowires have a well-defined hexagonal facets with surfaces. It is also very interesting to note that the diameter of this nanowires in the lower portion is lower than the upper. So this upper portion diameter is increasing as we increase the distance between the source module and the substrate. From position B, we got some more interesting morphologies that we got this aligned zinc oxide nanonails on whole substrate surface. We can clearly see that the upper portion of these nanonails shows a perfect hexagonal facet, which is because of the crystal structure of zinc oxide. And these nanonails are grown in very high density, as we can see from the low magnification images. In addition of this aligned nanonails, we also got the upper portion of this nanonail, some coral-like structures, which is made by this nanonails. So maybe thousands of nanonails are together and they made these coral-like structures. Because this coral-like structure, we think behind the formation of this coral structure, we thought that this coral structure was originated because of some thickness on the upper portion of our zinc oxide nanonails, and it grows oxidized and grows in this form. In addition to this, the corner portion of our substrate, we got some zinc oxide nanocombs also. These nanocombs are perpendicularly, these nanocombs are also made by this zinc oxide nanonails. We can see clearly in this picture and this picture that the zinc oxide nanonails, these nanonails are parallel attached with the zinc oxide nanonails or nanosheet at one corner and make this form-like structure. At position C, we got also this nen-like structure, but this is we can say inverted cone-like structures. These structures also originated in very high density on the whole substrate surface, but the alignment of these nanonails are a little bit poor. They are not fully aligned, but they are partially aligned to the substrate. In addition of this partially aligned zinc oxide inverted nanocones, we also have this cone-like structures on the outer surface of our substrate. Interestingly, we can see that these nanocones have one side this we can see this is not nanocones, but this is zinc oxide nanowires on one side. These nanowires are not uniform because of I think because of the distance between the substrate surface and this source material is long. So the zinc concentration was not enough to build this nanowires in perfect form. Also, we got some hierarchical zinc oxide nanostructures on this substrate. These hierarchical nanostructures are four-fold symmetry and which are made by this zinc oxide inverted nanocones. For detailed structural properties of our nanostructures, we did some TEM observations. And from this TEM observations, this TEM observation A and D is from the structures we grown at position A, while this C is the structure is from the position B. And from this structures, the general morphology of our FESM images is very consistent with these TM images. And we also did some HRTM images of this circuit portion of this nanolens grown at position B. We got that these nanolens have grown along the 0001 direction, and it has a perfectly hexagonal face. Because the lattice distance between the two fringes is about 0.52 nanometer, which is equal to the lattice constant of zinc oxide. So we can predict that our grown nanostructures are purely hexagonal with vertices. The crystallinity and crystal sizes of our grown nanostructures was observed by XRD pattern, and we got that this XRD all the nanostructures are grown along the C-axis direction. To know the optical properties, we did some Raman scattering and room temperature photoluminescence measurement. So in Raman scattering, we got only one peak at 437 centimeter inverse, which is the high optical phonon of E2 mode. This peak is the characteristic peak for Woodside hexagonal. So in all the cases, we got a dominant and sharp this E2 mode, which confirms that our grown nanostructures are Woodside hexagonal with good crystallinity. In room temperature photoluminescence spectra, we only got a strong and sharp UV emission in all the cases, and without any green emission or different emission. From this room temperature photoluminescence spectrum, we can confirm that our grown nanostructures have excellent optical properties and very less structural defects. To know the concentration of zinc and oxygen inside the reactor during the reaction process, we did some simulation, and we got that as the distance between the substrate between the source material and the substrate increases, the oxygen concentration is increases, while if we increase the distance between the source material to the substrate, the zinc concentration is decreasing. So we also did some more experiment to verify this whether we are getting at different oxygen concentrations the same results or not. So we did some more experiment, and we choose some 1.5:1 oxygen and nitrogen ratio, and 2:1 oxygen and nitrogen ratio, and at least 1 oxygen nitrogen ratio. And we observed at position C, we got previously I described that we got this inverted nanocones structures in a high density. But when we increase the oxygen concentration, we got this micro rods on the substrate. Even these micro rods are grown in very high density on the substrate, but the structure is from nano is transferred from nano to micro. But when we further increase the oxygen concentration to keep constant up to this nitrogen concentration, we got at 3:1 we got this coaxial shaped zinc oxide nanorods on the whole substrate surface. Also, to check the substrate effect on this reaction, we also did some experiment on different substrate at the same reaction process parameters. And we got that when we apply the same process parameter on the silicon substrate, we are getting this single crystalline, this hexagonal shape zinc oxide nanowires in a high density on the whole substrate surface. We can see clearly that these nanowires are not aligned, and but the shape of these nanowires are perfectly hexagonal. In case of steel substrate, we got this nanonails, and in case of aluminum substrate, we got this aligned nano rods, not nanonails or not nanowires, at the same experimental process parameters. So, in conclusion, I would like to say that we grow various zinc oxide nano adds nanostructures on the substrate without any help of any inverter catalyst or catalyst, just using zinc powder and oxygen gas for the source of zinc and oxygen. And the detailed experiment, detailed structure characterization indicated that our grown nanostructures are semi-crystalline with a perfect crystallinity, with a good crystallinity. And our grown nanostructures are showing excellent optical properties, as I showed in the previous discussion. And also the nanostructures of zinc oxide is quite dependent on the growth mechanism of process variables such as oxygen, zinc content, and so I want to acknowledge the Brain to Reactor project in 2006, and myself is thankful to CALEC for its graduate research fellowship program, and also I would like to say thanks to my Professor and Professor In for their proper guidance and kind cooperation. I would like to thank my all colleagues, Mr. Tong, Mr. Hassan, Mr. Park, Mr. Kim, Mr. and Dr. N. for their friendly behavior. And also I would like to thank Professor Saw for SPRC for their help in the presentation. Thank you.